Okay, so disk and shell method, it's again kind of useful in 3D printing. When we're 3D printing stuff, we kind of work in a 2D plane and work our way upwards. So if we're stacking a bunch of two-dimensional shapes on top of each other in order to create objects, whether that's plastic, or in this case chocolate, or anything else really, we can build whatever shape we want. If we cut another shape out of our two-dimensional cross-section, then we can create functions that are hollow, such as this object here. If we're revolving around a horizontal line, usually we prefer this method. If we use this method and we have a y function with an input of x, then we won't have to change our input and output if we use this method. So what we're really doing is we're taking one area of a circle with a radius, that's our distance from our axis of rotation, to our outermost function. And then cutting out another circle, so this hole inside, with our radius from our axis of rotation to our innermost function, in order to create our two-dimensional cross-sections. If we stack infinitely many of those together, we end up with a three-dimensional shape. Over here with shell method, we're creating cylindrical shells with a height that is our change in y, and then a distance around the shell of 2 pi r, so that's the circumference of this large circle on top. And if we stack infinitely many of those together, we end up with three-dimensional shapes as well. So in the shell method, we're revolving around a vertical line. We need to add r, which is our distance to our axis of rotation from the line that we are right now. We need an h, which is our difference in our y values of the top function and bottom function for the shape we want to construct. And a w, which is our infinitely small dx. As long as all of our functions are y in terms of x, we can use shell method without having to change inputs and outputs as if we're revolving around a vertical line. It is possible to use this method for revolving around a vertical line and shell method for revolving around a horizontal line, but we would need to change our inputs and outputs. Any questions on this method or shell method?
No.
All right. We also have volume by cross sections. Because any volume is really a two-dimensional cross-section times the height. If we can have an area times the height, we can keep changing the size of the areas as we stack them on top of each other, which is what we saw in the 3D printing. So our general form for the volume of any shape is the integral of our area times our depth, or our height, from height 1 to height 2. And with that, we could start to construct different objects with just the base of an object as we're stacking cross-sections on top of each other of different shapes. So here I've got a base that is a semicircle of root 25 minus x squared and the x-axis. If cross-sections perpendicular to the x-axis are squares, then we can start building those squares popping outside of the page. The side in the xy plane would be length y. The side popping out of the page would also be length y since these are squares. And we would integrate from -5 to +5, the points where we hit the x-axis, in order to keep stacking these on top of each other. Any questions? Volume by cross-sections?
No.
All right. So let's try a couple. Nope. There we go. Alright, so I've got this region here in the first quadrant enclosed by 2x and x squared. The first thing they want us to do is to find the area of R. So if I want to find the area bounded between two curves, Kyle, what do I need to do?
To use this method?
In this case, we're just looking for area, not volume, so not this method yet.
So we do the integral of 0 from 0 to 2 and 2x minus x squared.
Okay, integral from 0 to 2 of our top function minus bottom function. Looks good. So our top function is the 2x, bottom function is the x squared. So for part A, so I guess we'll write up here. Part A. Integral from 0 to 2, 2x minus x squared in terms of x. Okay, so this is without a calculator problem, so we're going to need to do this by hand. Kyle, I'm going to have you keep going. What happens if I integrate?
X squared minus x cubed over 3.
Okay, I'm integrating from 0 to 2, so if I plug in my bounds.
Since it's 0, so that cancels out. So it's 4 minus 8 over 3.
Okay, 4 minus 8 thirds. 4 is 12 thirds. That's 12 thirds minus 8 thirds is 4 thirds. Alright, for part B, region R is the base of a solid. For the solid, at each x value, the cross-section perpendicular to the x-axis has an area of the sine of pi x over 2. I want to find the volume of the solid. Okay, we're over to Andrew next.
Uh, uh, so our area is sine pi over 2x. So our volume should be a of x times r.
Okay, a of x times the depth of each value. Okay, so we've got an area that's popping up out of the page, which is some sort of sine function. But we also have an infinitely small change in x, right?
Yes.
So I've got something that looks like this. Each one of these parts that's popping out of the page is going to be popping out at a set height. So these really look like kind of rectangles at any one point. Popping out of the page. The area itself, so that part in yellow, is this sine function. If I'm going to integrate, what am I going to integrate from?
The sine function times the 2x minus x squared.
Sine function times. Okay, that area is already the piece inside, so the difference in my y values times some value is giving me this area already.
Okay.
So if I already know what the area for the yellow space is, and then I just need to multiply it by its depth. So what's the depth?
dx.
Dx, perfect. Okay, and we're integrating from what x value to what x value?
2 to 4. I mean 0 to 2.
0 to 2. Okay, so we're going to plug this in. This is the integral from 0 to 2 of the sine of pi x over 2 dx. Okay, Andrew, sticking with you. So for this, If I integrate the sine of pi x over 2, what's going to happen?
Then it will be negative cosine pi 2 over pi.
Negative 2 over pi, okay.
Cosine of pi over 2x.
Okay, from what value to what value?
0 to 2.
Alright. So we're going to go ahead and plug that in. If I plug in 2 right now, and this would be the cosine at pi. What's the cosine at pi?
Negative 1.
Okay, so this would be negative 2 over pi times negative 1 minus negative 2 over pi times the cosine at 0, which is
1.
1. Okay, so this is positive 2 over pi plus 2 over pi, or 4 over pi. And we're not given units, so we can stop there. Okay, for the last one, back to Kyle. Another solid has the same base, but for this solid, cross-sections perpendicular to the y-axis are squares. I want to write, but we don't need to evaluate an integral expression for this solid. So I'm going to draw a picture really quick. Our cross-sections perpendicular to the y-axis are squares. Cross-sections perpendicular to the y-axis are squares. So something like this.
So v is equal to the integral of 0 to 2, since it's a square, so ax squared dx.
Okay, so right now we're perpendicular to the y-axis, not the x-axis anymore, so I'm going to zoom in a bit. So that means our infinitely small part of this is actually a change in y. So if that's true, then I should be integrating from what to what?
From 0 to 4.
From 0 to 4, okay. So that's our first part. For part C, we're going to integrate from 0 to 4 since we are in terms of y. Okay, then I need an equation for the area inside. I said cross-sections perpendicular to the y-axis are squares. And we've got two functions here. Y equals 2x for this first one here in blue. And then y equals x squared for the second one in green. If I wanted to find this distance from here to here, what would I need to do?
Not find it and not integrate. So minus 2x minus x squared.
Okay, it would be, except 2x minus x squared is going to give us a distance vertically, not horizontally.
Oh.
So it's not my change in y's, it's my change in...
Oh, so do we solve for x?
Yes.
For each one?
Okay, we need our integral to be in terms of y's, so we're going to need to solve for x. So for our first one here in blue, this function is really x equals...
y over 2.
Y over 2, and in green, this function is really x equals...
The square root of y.
Square root of y, okay. So then, this distance here in red between them is going to be what?
Y over 2 minus square root of y.
Which one's bigger?
Y value. Square root of y.
Square root of y, okay, so this should be square root y minus y over 2. And because this is a square, this distance from here to here is also root y minus y over 2. Okay, so if I go in, this is a square, so when we multiply both of those together, I'll get root y minus y over 2 squared. Okay, so I've got the area times our depth, and we're ready to integrate. Oh, never mind. Right, but do not evaluate, so we can stop there, actually. Any questions on any part of this?
No.
All right. I'm gonna quickly flash all of our disk shell method stuff one more time for Sarah who just joined. So let me go back a bit. Okay, Sarah, quick review. Anytime that we want to construct a volume, what we're really doing is multiplying a bunch of two-dimensional cross-sections together. So if I take this 2D cross-section of a circle and multiply times the height, I end up with the volume of a cylinder of pi r squared h. If I wanted to use the same principle for any irregular shape, then I could keep stacking differently sized circles on top of each other in order to create any shape you want. So we could say that our volume of any 3D shape is really a two-dimensional area that's a cross-section that's flat times our depth or our height from height 1 to height 2. And if those areas are changing in order to create some shape that's not just a cylinder or a box or some basic geometric shape, then we would integrate instead so that we can multiply those functions together as they change. So our example here was this base, which is a semicircle enclosed by the x-axis. If I wanted to form cross-sections perpendicular to the y-axis that are squares, then my base that's in the xy plane is y. The part popping out of the page is also y. So my area is y squared. And I would multiply that by a dx as x changes from -5 to 5. Okay, then I can substitute for y. So because we were told that y is root 25 minus x squared, we can plug that in. The square root and the root cancel, and I'm left with an integral that we can solve to get our total volume when we stack all of those shapes on top of each other. Okay, so this is a principle that's used in 3D printing today. Stacking a bunch of two-dimensional shapes on top of each other, whether that's with plastic or with chocolate, with metal like bronze, or there's a group in Hong Kong doing this with human organs, so planting a bunch of cells on top of each other and then burning gel solution so that they can start to fuse together. We can also use what's called disk method and shell method to spin around an axis of rotation. So if you want to spin around a horizontal line, then without changing your inputs, we can use disk method. Spinning around a horizontal line would be creating a two-dimensional circle with an area of pi r squared. That r is your distance from your axis of rotation to your outermost function. And if you want to make it hollow, we can cut out a second circle of your pi r squared, where r is your distance from your axis of rotation to your innermost function. And then stack those on top of each other from your start point to end point. With shell method, we can spin around a vertical line by getting our distance between two y values, multiplying by 2 pi r. That's the distance of a circumference that we would spin that line around our axis of rotation for. And then multiplying by our width of each toilet paper roll, each infinitely thin cylinder that we've created. If we stack infinitely many of them together, then we create a smooth volume that we can spin around a vertical line. Okay, Sarah, any questions on volume stuff?
No.
Okay. So let's go back to some problems then. Alright, another no calculator. Part A, we're finding the area of region R. I did Kyle last time for this, so Andrew, I'm going to jump over to you. For part A, if we want to find the area of region R, what do we have to do?
Square root of integral from 0 to 4 square root minus x over 2 dx.
Okay, the area of any region between two curves is our top curve function minus bottom curve function from our start point to end point in terms of x. So that should give us the area. We don't have a calculator for this one, so we need to keep going from here. So what's going to happen when we integrate?
Then it will be 2 over 3 times x to the 3 over 2 power minus x squared.
X squared over
4 over 4.
Okay, from 0 to 4. Alright. Well done there with the oral part. I know that's different than Korean. So if I plug this in as 4, what's going to happen?
Then it will be
Okay, the way
square root of 32.
Okay, so the way I like to do these is I'll do the bottom part of the fraction first. So if you take the square root of 4, what do I get?
2.
2, and then cube it?
8.
8. Okay, so this is really 2/3 times 8. Okay, for the next one, plug in 4 in here. I'll get 16 over 4. Or 4. Okay, when I plug in 0 for our lower bounds, I'm going to get 0 for both of those. Okay, so this is 16/3 minus 12/3 is how much?
4 over 3.
4 over 3. Okay, part B. The region R is the base of a solid. Cross-sections perpendicular to the x-axis are squares. So I want to find the volume of the solid. I'm going to jump to... Oh, okay, we just lost her. We'll go to Kyle then. So cross-sections perpendicular to the x-axis, that's going to look like this, are squares. So if I've got cross-sections perpendicular to the x-axis and they're squares, so I've got squares popping out of the page that look like this. How
would
wide?
This be like,
oh, go ahead.
oh, sorry. Would this be similar to the previous example?
Similar. So we're creating cross-sections.
Oh, okay.
Alright, so this space that I've just drawn in yellow is our infinitely small depth. And how wide is that depth? So,
D.
right?
Yeah, dx.
Dx, okay. And then cross-sections popping outside the page we said are squares. So as long as I know what the distance from here to here is in the xy plane, then that would be the same distance from here to here popping out of the page. What's the distance from here to here, so between the functions in the xy plane?
Is that square root x minus x over 2?
Perfect. root x minus x over 2. And that's going to be the same on the other side then, since this is a square. Alright, so if I wanted to write our equation then what will our equation look like?
It's just r. Wait, is it 2 pi or?
Okay, we're just stacking a bunch of cross sections on top of each other. We're not spinning around an axis of rotation, so we don't need this Grisham method.
Okay, so so r is equal to the integral with the bounds of 0 to 4.
Okay. Okay, we're not getting the area of r. So we got the area of r in part A. Stacking a bunch of cross sections on top of that region R. So in this case, we're looking for a volume V. Okay, so V is equal to integral from 0 to 4 of what?
Square root of x minus x over squared. Oh, x over 2. Put them inside parentheses and squared dx.
Okay, we're squaring it because this was a square, and the area of that square is one side times the other side, so looks good. Okay, then we just need to solve this. So let's go ahead and square this out first, I think would be the easiest way to do this. So what's root x times root x?
So it's just x.
X. Okay, minus 2ab, so 2 times root x times x over 2. And then plus b squared. B is negative x over 2, so negative x over 2 times negative x over 2 is positive
X over 4.
Really close. Positive x to what power?
Squared.
Squared over 4. Okay. In terms of x. Alright, then we need to integrate this. So we'll go through and integrate normally. What happens if I integrate x?
Just x squared over 2. Minus 3 over 2 plus 1, that's 5. 5 over 2. So 2x over 5.
Raised to the power of
5 over 2.
Okay.
Plus x cube over 12.
Okay, we're going from 0 to 4. So last step.
4 squared is 16 over 2, which is 8.
Okay.
Minus 2x. X 4 to the power of 5 over 2.
Okay, so without a calculator, do the bottom part first. So we're going to take the square root of 4 first. What's the square root of 4?
16.
Oh, square root of 4, not 4 squared.
Oh, square root. 2.
2, and then raise that to the 5th power. So 2 times 2, 5 times.
2 times 2 times 2 times 2 times 2 times 32.
Okay.
Over 5. 32 over 5.
Okay, and then 4 cubed.
4 cubed for 5. 4 is 16. 16 times 4 is 64 over 12.
Okay.
That's, yeah, 64 over 12. If we add, and maybe use a calculator.
Okay, we don't have a calculator, so we'll have to do this without one. But we can reduce this. So both of these are divisible by 4. If I divide by 4, this will be 16 over 3. Okay, so now I've got, if I want to get a common denominator, what would I have to use?
The greatest common factor.
Okay,
So
which is
15. 15.
15. Okay, what is 15 times 8?
15 times 8. 15 times 4 is equal to 15 times 8 is equal to 120.
120 over 15. Okay, minus, I've got 64 over 5. If I multiply by 3, so that's 64 times 3. 60 times 3 is 180. 4 times 3 is 12, so that's 192 over 15. Plus 16 times 5. 16 times, yep, 16 times 10 is 160, so half of that is 80, so I've got 80 over 15. Okay. 120 plus 80
120. Oh, 200.
minus 192.
8.
So I've got
Over
8
15.
over 15. Alright. Any questions on A or B? Alright, last one over for Andrew. We want to write but not evaluate an integral expression for the volume of the solid generated when r is rotated about the horizontal line y equals 2. I'm going to redraw a new graph down here, maybe. I want to spin around this horizontal line y equals 2. Andrew, will this be dis method or will this be shell method?
Disk method.
Okay, this is dis method. You're right. Why is this dis method?
Because it's rotated horizontally by a horizontal point.
We're rotating around a horizontal line.
Oh, yes.
Okay. What's our formula for dis method?
Integral bound a to b. R1 squared minus R2 squared, where R1 is further is the distance between the rotation point and the function.
Okay. So this case.
And R1 is.
Sorry. In this case, R1 should be equal to this line here then. So you told me the distance between our axis of rotation and the outermost function. So what would this R1 be?
2 minus x squared.
Okay, 2 minus minus what? Sorry?
X over 2.
X over 2, okay. And then we're also going to have a smaller R2, which is our distance from our axis of rotation to the innermost function. What's that distance?
2 minus square root of x.
2 minus square root of x. What's our A and what's our B?
Our A is 0 and our B is 2.
A is 0, B is not 2?
4.
4, okay.
4.
Because we're still integrating in terms of x. So final answer for this one would look like this. V is equal to pi times the integral from 0 to 4 of R1, 2 minus x over 2 squared, minus R2, 2 minus root x squared in terms of x. Said write but do not evaluate, so I believe we can stop there actually. Any questions on this one?
No.
Okay, Kyle, you good?
Yes.
All right. Let's do one more of these, but maybe with a calculator. So I'm going to scroll up. Something more recent. 2015 is recent enough. Okay, I've got two functions here. Hold on, I think we've done this one already, haven't we? I feel like this is familiar. I'm going to skip this one too.
I don't think so.
You don't think so?
Yeah.
Maybe I did this with AB. Let's go ahead and do it. We've got time. So,
Okay.
we've got two functions here, f and g. We have two regions here, R and S, enclosed by the graphs of f and g. So the first thing they want us to do is find the sum of the areas, regions R and S. Kyle, in general, how do I find the area between two curves?
You find two terms.
Area between two curves.
You integrate. How do you call this? You integrate it? Yeah.
Okay, I'm going to integrate.
Integrate.
Okay, I would integrate from a start point to an end point of, what am I integrating for the area between two curves?
Fx and gx.
Okay, which is the top function minus the bottom function. My problem here is our top function and bottom function actually change.
So should we separate it? So since
Right.
0 to 2 to 4, that means I guess the midpoint could be 2.
Okay, it's not the midpoint, but we'll be able to calculate. Since this is with a calculator, we can calculate that intersect.
Okay.
Okay, so I'm going to set this up again. I'm going to define this point as our intersection point, which is our point, I'll call this point A. Okay, we're going to integrate from what to what?
From 0 to 2 to...
Okay, so that's from x equals 0 until x equals...
3.
3 would be way out here.
1.
Okay, we don't know what A is yet, but we can integrate from 0 to A. We'll calculate that in the calculator later. You said we needed to split this integral up into two separate integrals, right? So that's what we're doing right now. So for the first one, to get region R, I'm going to integrate what function minus what function?
Fx minus gx.
Okay, we'll verify that really quick by plugging in... we'll plug in some value really close to 0 and see which function's actually on top. It's this graph, actually. So we have to graph anyways. Okay, in the graphing calculator, if I want to start graphing functions, what do we need to hit first? So, what button?
Y is equal to...
Okay, y equals... I'm going to type in both of these functions, however, I'm going to move over to the left and change one of these to be bold so that we can figure out which one's on top. So I just moved to the left where this line is and hit enter, and that changes the way that we graph that line. Okay, so I'm going to graph 1 plus x plus e raised to the x squared minus 2. Oh, minus 2x, sorry. Okay. And gx is x to the 4th minus 6.5 x squared. Plus 6x plus 2. Okay, so y1 right now is f, and y2 is g. Okay, I'm going to graph this on an axis that shows us from 0 to x equals 2 at least. So I'll go to a little bit beyond what we need. And then I also need to see from 0 to 4 when they intersect. So again, we'll go a little bit beyond what we need. And we'll graph that. Okay, so it looks like f of x actually starts as the bottom function, based on our graph from our graphing calculator. Okay, so with that in mind, what should our first integral look like? I'm going to jump over to Andrew, I think. And then I'll grab Kyle again. Maybe for the second integral, and we'll get Andrew again for B. So Andrew,
Yes.
first integral should be from what to what?
From 0 to a, and it should be gx minus f of x.
Okay, gx minus f of x in terms of x. Okay, Kyle, I'm going to add a second integral from what to what?
From a to 2
From a to 2 of
f of x minus g of x dx.
f of x minus g of x dx, okay? Then I want to find the sum of the areas, which means we need to calculate a. How do I calculate an intersect in the graphing calculator?
Should we put them in the list or something like that?
Don't need to, since we've already got them graphed.
Also, like, since y1 is equal to f of x,
Right.
that means we could do the integral thing.
Okay,
Math 9.
So we can calculate, actually. So if we hit second calculate and intersect, and we've got an option for this directly. So we need to ask for a first curve, a second curve, and a guess. And that's because we could be graphing 10 functions at the same time. So this is the first curve that I want to intersect. This is the second curve I want to intersect. My guess is closer to this intersect than this one or this one. So my calculator should give me the intersect that's closest. So if I guess right here, it should give us the right intersect that we want. Okay, our intersection was at 1.0328319. And I'm actually going to copy all of that because that's not our final answer. So I don't want to round at all. So I'm going to hit second quit x store as alpha a. And now whenever I need that value, I can use that as a. So for example, 2 times a gives me an exact value without needing to round. Okay, I'm going to copy this number really quick. So as long as we define this here, a is on the interval from 0 to 2 not included. And then a is equal to 1.0328 31888. Okay, so that tells them how did I calculate the intersect? I found the point where the x value, where our f of x was equal to g of x between 0 and 2. And then we give the number. And now I don't ever have to use it again. I can just cite it as a. Okay, so now I need to go back and find the integrals. So I'm going to go back to our graphing calculator. And now, Kyle, if I want to integrate, what can I do?
Math 9.
Math 9. Okay, so now we're ready to do that. So I'm going to integrate our equations. This is g of x minus f of x. G of x for me is y2. So this is variables, y variables, function y2 minus variables, y variables, function y1. I'm going to integrate in terms of x from x equals 0 until x equals a. Okay, so our first integral is 0.997. Actually, I don't need to type this yet because it just says find the sum of the areas. So I can just set this equal to and then give an answer, and that should be okay for the AP exam. So I'm going to call this region R plus S is equal to, and then region R plus S is equal to, and I'll give our final answer down here. Okay, so I'm going to store this value as r, in case we need it again. And then I'm going to add region S. So math 9, I'm going to integrate variables y variables function y1 minus variables y variables function y2 in terms of x from a until 2. Okay, and we'll store that value as region S. Okay, so r plus s then is this. Okay, copy that over here. Any questions on what we did? All right.
No.
Andrew, use you predominantly for B since Kyle was predominantly A. Region S is the base of a solid. Cross sections perpendicular to the x-axis are squares, and I want to find the volume of the solid. Okay, we're only doing region S for the base. Cross sections perpendicular to the x-axis are squares. So that looks like this. Okay, I've got the space here in yellow. How wide is the space here in yellow that I'm drawing right now?
dy? Oh, no, never mind.
Close. Okay, this space here in yellow is what?
dx.
Dx, okay. And then this area here in blue.
Oh, y squared.
Okay. So this is going to be based on the difference in our y values for one of our sides, but this is a square that's popping out of the page, right?
Yes. So it's g of x minus f of x squared.
Right. G of x minus f of x squared. All right. So I got something like this. And you said this is for our side lengths. F of x should be on top, I think. F of x minus g of x. So for part B, our volume should be equal to what?
Integral from a to 2 time parentheses f of x minus g of x parentheses closed squared dx.
Perfect. And then because we've already got a defined and f of x were given, we should be able to type this in our calculator, get an answer, and we'll be done. So this is math 9. We're going to integrate f of x minus g of x squared. So this is variables y variables function y1 minus variables y variables function y2 squared in terms of x from a to 2. okay, is 1.283. Redraw that 8 really quick. Alright. Awesome. Okay, h is the vertical distance between the graphs of f and g in region S. I want to find the rate at which 8 changes with respect to x when x is 1.8. Okay, over to you, Kyle. First, what is the general form of h then? So h of x is equal to what?
So, is it the difference between g of x and f of x?
Would be except we're in region S, not region R. So this is the
Oh.
difference between
F and g.
f and g. Okay, so that's f of x minus g of x. Okay, I want to find the rate at which 8 changes with respect to x. If I want to find the rate at which a function changes, what do I need to do?
Derive.
Derive. Perfect. So my derivative of h should be equal to what?
Derivative of fx minus derivative of gx.
Perfect. And I need to do that when x is 1.8. So this is h prime 1.8 is equal to f prime at 1.8 minus g prime at 1.8. And we'll go into the calculator and calculate those derivatives. Okay, so if you have math, your 8th option down is a derivative. So I'm going to derive variables, y variables, function y1 is our f again, in terms of x at the value 1.8. Okay, and we'll store that as y. Okay, then we'll do the same thing for g. So I'm going to hit second entry twice. That'll bring back what we typed in last time, and I'm just going to change this y1 to y2, deriving y2 in terms of x at 1.8. And I'm going to store that value as z. Okay, so I want y minus z right now. Should give us h prime at 1.8. Or negative 3.8117. Okay, I'm going to copy this really quick. Negative 3.8117238486. Alright, any questions on the last one there?
Oh, no.
Okay. I think that's pretty much it as far as the calculus AB stuff goes with volume and area. We are 1 hour in. If you guys want, we can take a look at a parametric one, so I'll go find one from BC. If not, we can call it today. How do you guys feel? Do you guys want to try a polar or parametric equation, or do you want to just stop here?
Can we try one polar?
Polar, okay. So let's do... 13 FRQ. There we go. Okay, can you guys still see?
Yes.
Cool. Hopefully, oh, there we go. Okay, so here's a polar. Okay, I can't write on this though, so let me copy this over to a Word document that will let us write, and we'll do that from there. Alright, hopefully this will let me write on top of this without actually moving that object as a mouse. Alright, so for the first part, I've got this region S bounded by our graph of our polar curve from 0 until square root pi, shown in the figure above. First thing I want us to do is to find the area of region S. Kyle, what's the area of a polar equation?
The area is 1/2 the integral of a to b r squared d theta.
Okay, that's good. So we are going from 0 until the square root of pi first. So that's going to take us from 0 until pi plugged in for sine, which will get us from 0 to 0 again. So it does look like we only trace this once. So that should be good. From 0 to root pi of 3 root theta sine theta squared. Squared in terms of theta. Okay, we'll type that into a calculator and get our area. So okay, so I'm going to keep this in the rectangular for now, just so we can get our integral there, and we'll type in 3 root x times the sine of theta squared. And for y1, so this is 0.5 times the integral of variables y variables function y1 squared in terms of x from 0 until square root of pi. And that should give us our area. Okay, so I've got 3.53 for our area. Okay, over to Andrew for part B. I'm looking for the average distance from the origin to a point on the curve on our interval. What do I need to do? What is the distance from the origin to a point on a curve? In general, what's the variable?
Radius.
The radius. Okay, so this is really looking for the average radius from 0 to root pi.
So it's 1 over root pi times integral from 0 to root pi of 3 square root theta sine theta squared.
Okay. So of r theta in terms of theta, looks good. And we can plug that in. So we already have our function r right now is our variable y1. So this is going to be 1 over the square root of pi times math 9. The integral of variables, y variables function y1 in terms of theta, which for us is in terms of x because we're still in the rectangular, from 0 to root pi. Okay, so I've got 1.5799. I'm going to write as 1.580. No units. Any questions on anything from A or B?
Oh, no.
All right, for C, there is some line with a point. There is some line through the origin with a positive slope m, dividing the region S into 2 regions with equal areas. So it's going to look like this. Some positive. Oh, what did I just do? Okay, I think I noted it. Try it again. Some line with a positive slope like this, dividing these into 2 equal areas. Okay, I want to write but not solve an equation involving one or more integrals. The solution gives the value of m. So what do I need to do first?
Did you divide the area?
Could I divide the
Okay.
area in 2? Okay, that is what I'm going to do first. So the point where we stop would give us our distance r, right? So we can get this distance, or at least get a formula for this distance, by saying that 1/2 of the area at that point where we split. Oops, sorry. 1/2 the area total is the area at the split point. Okay, so that should give us an equation that we could solve in order to get our radius r. And then we can set up a triangle relationship. So once we know r and we know theta, because this is a polar equation, then how could we find the slope?
Tangent.
We find r cosine theta, that's our x, and r sine theta, that's our y. We divide. y over x
And
that
we
we
divide
find.
them. Okay, cool. I'm gonna combine your two suggestions, I think. Because Kyle, I think you're onto something too. I think I just moved the picture in the background. I did. Okay. I was afraid of that. I'm back. I think so. Okay, combining your two suggestions. Kyle, you said you wanted to use tangent. The tangent of theta is equal to y over x. Would be equal to m, right? So if we know what theta is, then theta should be the arctangent of m, and that will give us an m in our equation that we could solve for. And we'll set up our equation. I want 1/2 of the total area to be equal to the area of the split point. What's the equation for our total area?
1/2 times the integral from 0 to square root of pi. 3 times square root theta sine the r, the r d theta, r squared d theta.
Okay, r squared d theta. I'm going to go ahead and throw those in parentheses here. Okay. I'm going to clean that up a bit now that we're zoomed in. Okay, so we've got 1/2 of that total area should be equal to our area at the split point. What's the equation for the area at the split point?
1/2 times integral from 0 to x.
Okay, 1/2 times the integral.
With 0 to some value.
Some value. So that value is going to be our angle at the point where the radius is what we want, right? And
Yep.
our angle is the arctangent of m. So I'm going to write the arctangent of m because that gives us a slope in our equation. Using a combination of what you gave me and what Kyle gave me.
Okay.
We don't need to solve for this, we just need to write an equation with m in it, so that should be fine. And what are we integrating?
R theta squared. D theta.
R theta squared d theta. Okay. Get this parentheses cleaner too. And we should be good. Okay, hopefully that's right. We'll check after this. So I haven't actually seen the scoring guides yet. Alright, so this is an addendum adding after the fact. We had some debate and a calculator mistake that made this a little bit longer than we thought for part D, but for part D, we've got k is greater than 0. There's an area of this portion S that's also inside the polar equation, r equals k cosine theta. I want to figure out what the limit is of our area as k approaches infinity. So we graph these really quick, this time in the polar. So we've got our first radius, which is 3 times the square root of theta. Polar. Okay, 3 times square root of theta times the sine of theta squared. And k cosine theta, which I'm just going to model really quick as we'll do 4 times the cosine of theta. Okay, I'm going to change our window to go from 0 until the square root of pi. Okay, and we'll graph that. So we've got our equation here that was in the graph, and our little circle out here. And as we keep building those circles more and more, let me do a zoom box so you can see what's going on. somewhere out here. So as we keep building those circles more and more, the cosine at pi over 2, which is not quite to the square root of pi, is going to give us 0 for our radius, and after we extend beyond that, we'll be in quadrant 4 for k cosine theta. So eventually, as k keeps increasing and we get bigger and bigger and bigger radii of that circle, then what's going to happen, I can model this with maybe throwing in a bunch more 4s here, is that circle is going to get closer and closer and closer to the y-axis as it comes down to hit 0. So if I add 2 more 4s in here, we'll be almost at the y-axis exactly. We keep getting closer and closer and closer. Okay, so as k approaches infinity, this line will get closer and closer to the y-axis, and I'm eventually going to enclose all of S. That's in quadrant 1. And if we enclose all of S in quadrant 1, then we'll look something like this. So as k approaches infinity, the area of k approaches the integral from 0 to pi over 2 of r theta d theta. And then we'll make this polar area, so that's 1/2 of r squared d theta, which is 0.5 times the integral of variables, polar r1 in terms of theta from 0 to pi over 2. Oops, I need to square that r1, don't I? Okay, so I've got it 3.32. Which we then checked afterwards and was correct. Really for this one we checked before because we didn't get it the first time. Then we came back and tried to figure out how we got there. But A, B, and C proved right.